Swayam Prabha. Digital India. Educated India.
Today we will be talking about configuration space and C-space obstacles. In the last couple of classes, configuration space and what is the requirement for configuration space. So today we will be talking about how to develop these configuration spaces for mobile robots in 2D and also for planar robots. So today's topic is C-space obstacles, that when we are having obstacles in 2D, then how do we expand the obstacles to make them C-space obstacles. Okay, that means that the obstacles become C-space obstacles and the robots become a point, and then we do path planning for a point in our configuration space. So very quickly, let's revise what we were doing in the last class, and then we will proceed into the details of today's lecture. So we said that the very basis of path planning is that the robot should not hit an obstacle. Okay, but that is so basically what we are saying is that it should not hit an obstacle. Now hitting an obstacle is essentially English language. Now mathematically, what does it mean? Okay, because at the end of the day, this is going to be a program or an algorithm that is going to determine whether the obstacle is hitting, whether the robot is hitting the obstacle or not. Okay, so the robot should not hit an obstacle essentially means that no point on the robot should interfere or be inside the obstacle or on the boundary of the obstacle. Now we started off by saying that the robot is a point robot and it has no physical dimension. Okay, so in the case of path planning in the earlier bug algorithms, we talked about bug 1 and bug 2 algorithms, where we did our planning, that we have obstacles and we have the robot here and we want to go to the goal point here. So this is my start and this is my goal, and we want to go from one point to another point. Then we simply said that in the bug algorithm, basically the robot goes in a straight line towards the goal, circumnavigates the obstacle, finds the leaf point, goes to the next obstacle, circumnavigates, and then goes to the goal point. Here we are making the assumption that this is a point robot. So please note that this is a point robot, it has no physical dimension. Okay, so it's very easy to check for intersection between an obstacle and a point. Okay, that means you know the boundary of the obstacle and the points which are inside the obstacle, and this point robot should not go on the boundary or inside the obstacle. Okay, that is not very easy, difficult to check by means just by using simple geometry. Now a real robot in the real world has physical dimensions. So if a robot has physical dimensions, then if we want to ensure that no point of the robot should interfere with the obstacle, that's not very easy. Especially for a serial arm, okay, which can have 6, 7, 8 degrees of freedom. Okay, so basically what we do is that we do not do the planning in Cartesian space or Euclidean space. We basically have to go to another space which is called the configuration space. Okay, essentially to ensure that no point of the obstacle of the robot interferes with the obstacle. Okay, so how do we do that? So basically we see that a real robot has physical dimension. So if this is a circular robot, okay, then it has a radius of r and it has coordinates x, y at the center. Okay, now we are saying that no point of this robot should hit the obstacle. This is my obstacle, so no point inside there should hit this obstacle. Now to enforce that is not very easy. Okay, so what we can do is we have to move from Cartesian space. This is Cartesian space. What I mean is this is x and this is my y, okay, axis. So this is Cartesian space in 2D Cartesian space. So planning here would be very difficult. So what we do is we convert this space we go from the Cartesian space to this C space or configuration space. So the question being asked here is that what is the minimum number of parameters required to specify all the points of this robot. Okay, now how can we define that? Now if you look at this robot, basically if I am given the center of points, center CG of the robot or the center point of the robot, and if I know that the radius is r, then for any point, okay, I know if I say that my x dashed y dashed is here, then if I know that r is the radius of the robot, then my robot is here. Okay, so this essentially means that these two parameters x and y, okay, is enough to specify all the points in the robot. Okay. So, this question how to specify all the points of the robot is answered from here, that if I just know x and y, and because I know that the radius is equal to r, then all the points of the robot are automatically specified. Okay. That means, if I go to another space which will have only these two parameters x and y, then I can do the planning in that space. So, the two parameters x and y are enough to specify all the points of the robot. Okay. So, this is two parameters, and these two parameters make up what we call the configuration space. So, when we say configuration space of the robot, essentially is the least number of parameters that are required to specify all the points of the robot. And the configuration space or C space, in short we call it C space, is the space of all configurations of the robot. And I hope you understand how this x y came and from where this x y came. Okay. So, it is not very easy to it is not very difficult to understand that if you just know x y and you know the radius, then every point is automatically known. Now, in configuration space, this robot is just a point. Now, why is it just a point? Because it only has coordinates x and y. So, it is a point. Okay. Which means the robot has shrunk to a point now, okay, in this space. So, if you look at Euclidean space here, let us take a very simple example. We have an obstacle like this, and we have a robot which is circular robot x y. Okay. Now, if I want to specify all the points of this robot, what we are saying is that we reduce this point to the in the configuration space to only the x y. So, now this robot has become a point here. Okay. Now, because this robot has become a point, the obstacle has to increase by an amount of r. Okay. So, what it basically means is what is the positions which the obstacle which the robot can go and sit on the obstacle. Okay. So, these are the limiting conditions. So, the robot can go only in these locations. Okay. It cannot go inside. Okay. So, now if I draw the position of the obstacle of the robot on the obstacle like this, and I take the center of the robot which is the x y, then what we will get is basically a line like this. So, there will be curves in the ends and this is going to be straight lines. So, what we are getting is the robot has gone down to a point, whereas this obstacle has enlarged by an amount which is equal to r, and it has become my C space obstacle now. Now, this is C space. So, this is my C space of the robot, and this is called the C space obstacle. So, this is called my C space obstacle. Okay. So, this is the meaning of C space obstacle, and this is also showing us how we move from the Cartesian space to the C space. Okay. Now, when we are doing path planning, basically we are doing the path planning for a more point now. Now, it is very easy to know whether this point is inside, okay, or it is on the boundary. It is very easy to do that, because you know what are the vertices of this obstacle now, the C space obstacle, and you know if this point is inside or sitting on the boundary. So, this point not hitting this obstacle. So, we come back to hitting the obstacle essentially means this point should not even be on the boundary of that obstacle. Okay. It should not be inside, it cannot go inside, and it should basically not go onto the boundary of the obstacle. This is the meaning of hitting the obstacle, and this is how we can very easily ensure that the point is not inside the obstacle, which also means the robot is not inside the obstacle. Okay. This is very easy to visualize here. Now, going further, we see that configuration space or C space is the space of all the configurations of the robot, and in this particular case x y is enough to specify the configuration space of the robot, and in that configuration space whatever is the shape of the obstacle, that is the C space obstacle now. Okay. Now, something to remember, please remember this, and this is something to understand, that the C space looks like the Cartesian space, but it is not the Cartesian space. Okay. What I mean by that is this space here is my Euclidean space or Cartesian space. Okay. This looks like this space. What I mean by looks like, because there is also an axis here, a coordinate system x and y, if I say they are 2D, and we also have an x and y here, x and y there. Now, these two spaces look like they are the same space. Okay. But they are not the same space. One is a C space, the other one is a Cartesian space. Now, they essentially look the same because we are having only two dimensions here, only x and y. So, it is only x y. So, it is looking like it is the Cartesian space x y. Okay. Now, we move further to look at the degree of freedom of a system. Okay. So, the degree of freedom of a system is the dimension of the Cartesian space, of the configuration space. Okay. Now, the minimum number of parameters required to specify the configuration is also called the dimension of the space, or so the dimension of the configuration space is also the DOF of the system. Okay. So, the dimension of the configuration space is the degree of freedom of the system. Okay. Now, in the previous case here, what is the dimension of the space? This fellow has only x and y coordinates. So, the degree of freedom is equal to 2. So, and what are those two? There is only x and y. Okay. So, the dimension of the C space is also 2, and the degree of freedom of the system, the mobile robot, is also 2. Okay. Now, if we have 3 independent mobile robots, so these are 3, let us try and understand the relationship between the configuration space and the degrees of freedom of a system if there is more than one system. For example, if we have 3 independent point robots, okay, having a total of 6 degrees of freedom. So, suppose we have 3 robots now. So, this is one robot, let us call it A, and there is another robot B, and there is another robot C. Okay, these are mobile robots and they are independent, okay, they are not connected in any way. Now, this can move in any direction, right. So, it has configuration space of dimension 2, which is x and y, or it has 2 degrees of freedom, which is x and y. Now, this also has x, let us call it xb and yb, this has also 2, and this fellow also has 2, that is xc and yc. Okay. So, let us call it xa, ya. Okay. Now, these 3 robots which are independent, something to note here is that they are independent, okay, and they can move independent of each other. These robots can move in any direction. Okay. Now, if we say that this is a system, then the total system has 6 degrees of freedom. Okay. Now, the total system has 6 degrees of freedom, and there are 3 of them which are having 2 degrees of freedom each. So, how did we get 6? So, each of these fellows have 2. So, 2 to 2 is equal to 6, and there is no connection between them. They are not having no constraints or between motion between the robots. Okay. So, these robots are not subjected to any constraint, which means that we simply add the degrees of freedom of each of the robots and we get 6, and 6 is the total degree of freedom of the system now. Okay. Now, something to note here again, there is no constraints between the motion, that means they are not connected in any way. Okay. So, going back here again, this had 2 degrees of freedom. What are those 2? X and y, which is very clear. Now, we are having 3 robots now, each having 2 to 2, and they are not connected in any way. So, there are 6 degrees of freedom now. So, this is 6 degrees of freedom, and there is no constraint between them. Okay. Now, if you try and answer this, that a physical robot has dimensions. Okay. It can translate, it can also rotate, okay, in 2D. Now, this robot, that a real robot, can translate and it can rotate. Okay. Now, how many minimum parameters are required to specify the configuration of this robot now? Okay. So, this is the question we are trying to answer. So, we said that a point has 2. Now, if we have 3 point robots, that is 6, but there are no constraints. Now, if we have a physical robot which can rotate and translate, then how many degrees of freedom does it have? Okay. So, how do we answer that question? Let us say we have a robot here. Okay, this is my robot, okay, and it has wheels which are there, okay, and there is, let us say, a caster wheel here. Okay, so, this is a caster wheel there. Now, this has differential velocities omega 1, omega 2, and we have a center point here. Okay, let us call this point P. Okay. Now, if I draw my axis, this is my x axis, that is my y axis. Okay. Now, this point P has coordinates x and y, okay, and this makes an angle of theta with the x axis. Okay. Now, the question is that I want to find out the degrees of freedom of this robot. Okay. It is a planar robot, it can rotate, and it can also translate. Now, if I want to find out the degrees of freedom of this robot, how do we proceed? Now, let us assume that I have I fix 3 points on this robot, and then find out that how many parameters are required, or the minimum number of parameters required to specify the position and orientation of this robot. So, I take 3 points. Now, the first point A, I put it here. Okay, this is my point A. Okay. So, the first point A I put, and it has coordinates let us say xa and ya. Okay. Now, this point A could be anywhere on this robot. Okay. There is no constraint on it. So, this could be anywhere. Okay. So, now we are saying that I have this point A which I have placed. Now, I take my point B, I take the point B and say that I take my point B here and put my point B here. So, and this point B has coordinates x b, y b. Okay. Now, the moment I put the point B, what would happen is, so the point B has coordinates x b and y b. Okay. Now, this point B, the moment I have put it, because point A is fixed, this distance between A and B gets fixed because it is a rigid body, okay, which means that distance A B now becomes equal to root over x squared x A minus x B squared plus y A minus y B squared. So, this means that because this is a rigid body, the moment I have put the point B, the distance between A and B is fixed now. Okay. Now, the B, now if I put a point C, now I have another point here, C could be anywhere, but the moment I put C, what is going to happen is that the distance between AC and CB will get fixed now. Okay. So, distance between AC, which is equal to x A minus x C squared plus y A minus y C squared will get fixed, and the distance B C is equal to x B minus x C squared plus y B minus y C squared. Okay. So, what we are seeing is that the moment we have put A was free, we could have put it anywhere, okay, but the moment I put B, this distance gets fixed. So, one kind of constraint comes into the picture, which is this one. Okay. The moment I put C, C could have been anywhere, but then the moment I put C, what happens is two more constraints come in. This is the first constraint, this is the second constraint, and this is the third constraint. Okay. Why? Because it is a rigid body. Okay. So, the moment I have put A B C, we have to satisfy these three constraints now. Okay. Now, each of A B C had three parameters each. So, A B and C was here. So, it is x C and y C. So, this was 2, this was 2, and this was 2. Each of those points have 2 parameters to specify, which we have seen why it is 2. So, total we have 2 plus 2 plus 2, which is equal to 6. Okay. But we have 3 constraints, so it becomes 6 minus 3, which is equal to 3. Okay. That means this body has 3 degrees of freedom, okay, and the dimension of the space of C space of this is also 3. So, dimension of C space is also equal to 3. Okay. Now, what are these 3 parameters? One is x y of this point, okay, one is the x y of that point P, okay, and the other is that angle theta, other is theta. So, x y and theta. Okay, this is my 3 parameters which I am getting. Okay. Now, something to understand is that although each of this had 2 independent degrees of freedom, x and y, but the moment you place them on the rigid body like that, what would happen is the minimum number of parameters minus the constraints that are there is equal to the degree of freedom of the system now. Okay. And so, the C space also will have dimension equal to 3. Now, so what are the 3 degrees of freedom? It is x, y, and the angle theta. Okay. Now, this kind of constraint are called holonomic constraints, and these constraints are a function of the configuration variables. So, we can write it in this form g q of t is equal to 0, which is equal to this one. So, these constraints are called holonomic constraints. Okay, this is a holonomic constraint, this is also a holonomic constraint. So, these are constraints that are expressed as a function of the configuration variables, and time also could be there. So, and they are written of the form g of q t is equal to 0. Okay. So, this holonomic constraints reduces the dimension of the system configuration space by 1 each. So, each linearly independent holonomic constraint reduces the dimension of the system configuration space by 1, which means that the dimension of the system configuration space was 2 plus 2 plus 2, because there were 6 independent parameters, okay, but we have 3 constraints. So, it becomes minus 3 is equal to 6. Okay. So, and this happened because they were holonomic constraints. Okay. Please note that this kind of constraints are called holonomic constraints, and they reduce the dimension of the configuration space by 1. Now, are there any other kind of constraints? So, if you look, if you think a little bit further, the robot with drive and steering, let us talk about this robot. We have another robot which is like this. So, this is a car. Let us say that this one is a car or an automobile that you see on the roads. So, it has rear wheel drives, and there is the steering angle. Okay, so this is my theta now. Now we have a point P which is on the center point there, and there is an angle between this and this. So there is an angle here. Okay, so this is my phi. Okay, so this has a robot with drive and steering. This is basically a car model. So there is a drive and there is a steering. Okay, so that's how a car can turn at an angle. Okay, now if you look at this figure, this is my x-axis and that's my y-axis. Now when this car is turning, okay, so we are saying that the car is turning. When the car is turning like that, is taking a turn, the velocity at that point here will have to be, so let me draw it. So let me draw it again. Okay, let us say the car is turning. Now if the car is turning like that, then the velocity at this point will have to be tangential to the curve there. Okay, so this is my velocity. Okay, so what we are saying here is that when this car is turning at a particular angle, at that point, okay, at that instant rather, the velocity is tangential to that curve. So velocity vector is tangential to curve at that point. Okay, this is the meaning when it is rotating. So similarly, when this fellow is turning a little bit more, then this angle, this will change, then this will change. Okay, so at every point there, when the car is turning, the velocity vector has to be tangential to the curve at that point. Okay, now now because this condition has to be satisfied, this is also a condition. Okay, but this is a condition on the velocity. Okay, so if this condition has to be satisfied, this kind of a condition is called a non-holonomic constraint. So these constraints are velocity constraints. What is the velocity constraint of this car, which is taking a turn? So when it is taking a turn, at every point on that curved path, the velocity vector has to be tangential at that point to the curve. Okay, so this is a constraint, and this constraint is written in the form q of q dot. Okay, and there could also be time. So this is called a non-holonomic constraint. So non-holonomic constraint. Okay, so these kind of constraints, which are velocity constraints, are called non-holonomic constraints. Now what does this constraint do to this vehicle? Okay, if you think a little bit, because this constraint is there, this car cannot go sideways. Okay, okay, it can go forward and it can turn only at a particular angle. Okay, it cannot go forward at all. It cannot go sideways. So the side velocity is equal to 0. Okay, so this constraint has ensured that the vehicle cannot go sideways. Okay, why? Because the velocity vector has to be tangential to every point in that curve. Okay, at that instant. Now this constraint has ensured the car cannot go sideways, but in terms of the configuration space, something to note here is that these non-holonomic constraints do not reduce the dimension of the system configuration space. So non-holonomic constraints are velocity constraints, and they do not reduce the dimension of C space. Okay, we will come to this when we talk about motion planning with kinematic constraints, but at the moment it's just enough to know that we have holonomic constraints and we have non-holonomic constraints. One are constraints on the velocity, which is non-holonomic, and in the case of holonomic, it is just in case of the position. Okay, so these are two constraints which are there for the mobile robots. Okay, so the configuration space here is 3, and the configuration space here is also 3. So here it is x, y, and theta. Okay, so now let us think a little bit more. Now the degree of freedom of a robot, or dimension of the configuration space of a robot with drive and steering, we just saw that the configuration is a specification of all the position and orientation of the local frame with respect to the global frame. So here I forgot, we can put a local frame here, we can put a local xy. So let's call this x r and y r. Okay, so essentially it's a relation between the local frame and the global frame. Okay, now the configuration space can be represented as t theta. So t theta in our case, t and theta in our case. So t was equal to x and y. Okay, now we talked about two frames, right. So, we had the car here, this was our car in the previous figure. If I draw it again, okay. So, here I put a local frame which is like this, okay. So, this is my R frame, and let us call this the I frame, world frame or global frame. So, essentially if you are trying to find the position and orientation of the car, that means you are trying to find the position orientation of the frame R. So, it is position plus orientation of R with respect to I. Okay. So, when I am saying I want to find the configuration of this robot, it is essentially saying trying to find the position orientation of the frame with respect to the global frame, and this has three parameters. One is the position t, which is x and y of this point P. Okay. The other is theta. Now, theta is the angle. Now, we know that the angle between two frames, okay. So, angle between frames is represented by the rotation matrix. Okay. So, this is a matrix, okay, between the frame I and the frame R is equal to cos theta minus sin theta cos theta. Okay. So, please note here very carefully that when we said t and theta is the configuration variables, t is simply x y, whereas theta is a matrix, actually it is the rotation matrix. Okay. So, the configuration can be represented by a set of t and theta, where t is the position and theta is the orientation, which is a matrix. Okay. So, both of this t and theta make up the position and orientation of this car with respect to the global frame. Okay. So, once we know R, because you know what is theta, then we can go in either direction. Okay. So, now let us proceed a little bit more today and see how to draw our C space obstacles. So, the objective of path planning problem is we are reducing the robot, a circular robot that can only translate, to a point, and then we are trying to find the path in space. Okay. So, let us look at these three examples. Is the objective of path planning problem is determining a continuous mapping, it has to be continuous, such that no two configurations in the path cause a collision between the robot and the obstacle. That is the objective of path planning. So, if you look at these three cases 1, 2 and 3, okay. In case 1, the robot is a point. So, robot is a point. Okay. So, the C space obstacle remains the same. Okay. And if you want to find a path, you can find a path like this and go from here to here. Now, in the second case, the robot has some physical dimension, let us call it R. So, when I make the C space obstacle, what I will do is I will increase the I am going to increase this by R, okay, and draw my C space obstacle. So, this one becomes like this. Now, it is very clear that at the bottom side there is no space, there is no free space. Okay. So, the free space is not there, which means the robot cannot go in that direction. So, if it has to go from here to here, it can go only this way, there is no other way. Now, in the third case, the robot is a slightly bigger size, and we again draw the C space obstacle by, this is slightly bigger. So, we draw it like C space obstacle is going outside now. So, like this, the robot is much bigger in size. Okay. Now, we see that the C space obstacle has actually covered this side also and this side also. Okay. Now, please note that as the obstacle has become bigger, the boundary has also shrunk. So, here the boundary has shrunk and it has become smaller. Okay. Please note that also. Okay. So, two things have happened. Number one, robot is a point, robot has become a point, robot becomes a point, obstacle enlarges, and workspace shrinks. Okay. So, please note in all the three cases that in the first case the workspace remained the same because the robot is a point. In the second case, the workspace became smaller. You can notice that this and this, the two rectangles are different, and the C space obstacle has become larger. Now, in the third case, the workspace has shrunk and the obstacle has become larger, and because of which there is no space now between where the robot can go from one side to the other side. Okay. Now, these obstacles are basically called C space obstacles. Okay. And by now it should become very clear to you that essentially why this is done, because if you just look at this now, okay, it's very easy to see whether there is a path or there is no path. Okay, it's very easy, and for us to see, and as I said in the past, in the last few lectures, that we can see, so it's very easy for us. A robot cannot see. It's a program cannot see. So for the program also, this is basically a geometrical problem, which means this is the boundary of the obstacle. The robot is a point. Is there any path? Is there any continuous function which is connecting the start point to the goal point, which is not intersecting with the obstacle? That is a geometrical problem, which the program has to solve. Okay, so this is what we mean by the path planning problem. So fundamentally, we need to make the C space obstacle. Okay, we need to draw it. So C space obstacle. Okay, we want to draw the C space obstacle. So let us draw the C space obstacle. Now, how do we draw the C space obstacle? Suppose we have an obstacle here. This was the obstacle, and this was the robot. We said that the workspace is going to shrink by r. So this is my r. So the workspace is going to shrink by r, which is easy, which is not very difficult to imagine. So it shrinks by r. But for this robot, how do we start drawing? Is we take the shape of the obstacle and place the robot at different locations. Okay, the boundary locations. So the robot can go to all these positions, okay, but cannot go beyond this. Okay, and then what we do is we connect the center point of the robot. So at this corner points, you can imagine that if you have a corner, okay, so the robot can sit here, and the robot can sit here, and it can also go at that point, can sit there also. So there is a curve there. Okay, that's how this corner point curve comes. Okay, so if you do that, then what we get is the C space obstacle is made like this. It gets enlarged, and now if this is my workspace, then what is free space? Free space is the workspace minus the C space obstacle. Okay, so that is the definition of the free space now, which is very easy again. So we have the workspace, which is the boundary, and minus the C space obstacle. So whatever is the free space, that is my free space. So if I want to go from here to here, I can go like this, or I can go like that, or I can go in other ways. Okay, now the program geometrically has to figure that out. Now, so the program also should be able to geometrically make the C space. So today's lecture, basically we are interested in looking at how to make the C space obstacle automatically. Okay, so this is how we proceed. Now in the previous case, this was a circular robot, so it was pretty easy. Now suppose we have a triangular robot, which is given like this. Now what we do is essentially note that the please note that the origin is here. Okay, so we have to track the origin as the robot is moving. So how do we start? We start off by saying that this robot can only translate. Okay, it cannot rotate. Okay, please note no rotations. So theta is fixed. Okay, so how do we start? We take it at the bottom corner here and slide it up like that. It can go maximum till here. Then it slides this side. Then it comes till here. Then it slides down till here. But once it comes till here, note that from here, because this surface is inclined, the robot can slide like this and come till here. Then it goes like this, and we close it. Okay, so this is the boundary condition on which the robot can go. This is the boundary up to which the robot can go. It cannot go anywhere beyond here. So please note that it is possible for the robot to go here. Okay, this is okay. Okay, and what is the shape of the C space obstacle? The shape becomes something like this. Now if I were to do this automatically, then we need to have some correlation. Now if you look geometrically, what is happening, the robot is a triangle, it's not rotating. Okay, so if the robot has, in this case there are three faces. Okay, it's a triangular robot. Now this side and this side are perpendicular. This is perpendicular, this side is perpendicular to the if this is my x axis, that's my y axis. This is perpendicular to the x axis, and that is perpendicular to the y axis. Okay, now these two faces, which are perpendicular to the x axis and y axis, do not cause any kind of inclination on the C space. But if you note here very carefully that this was inclined, okay, this face was inclined. Why was it inclined? Because this corresponds to one inclination here. Okay, that is this one. Okay, so there appears to be a correlation between these two now. Okay, so the correlation is that the inclined line on your C space corresponds to the inclined side of the robot. Okay, so in this particular case, there was only one inclination. So, what happened is there was only one inclined face here. Okay. So, geometrically you can correlate. Now, you can also correlate that this inclined face corresponds to which face on this side. So, if you look at that, then if this is my inclined face, this is parallel to this. So, if I draw a normal like that, okay, then this also will be normal like this. Okay. So, this normal here and this normal, or if I draw a normal on this side, let me draw the normal this side, then this normal is exactly on this side. Okay. So, let me draw it there. So, this normal to the surface is this normal actually. So, I know exactly where it is going to come also on this E space. Okay. Now, let us look at one more example. This was only one inclination. Let us look at a case of two inclinations. So, here I am saying that I am drawing a normal like this, this normal is here, this is my inclined face, okay, which is corresponding to that. Now, if we rotate the robot by some angle, let us rotate robot by 45 degrees. So, theta is equal to 45 degrees now, and we are getting this configuration. Okay. Now, again note that the origin of the robot is here. Okay. So, when the origin of the robot is there, we are going to track this point. So, exactly the same way we start from here, okay, and move it upwards. Okay. So, it is going to move up till here. Okay. It moves up till there. So, I get this line. Now, because this surface is inclined, okay, what happens, this fellow is going to slide up like that. So, it can slide till here. Okay. Then it moves this side and comes till here. Okay. Now, because this face is inclined, what will happen is it can slide like this now. So, the top line comes like this, the robot has come here. Next, it can move down till here. Again, because this side is inclined, this side is inclined, it can because this side is inclined, it can slide along that and come here. So, if you look at the locus of the origin point, what we see is that it is taking a trajectory which is something like this. It is going like this, like this, like this, like this, like this, like this, and like that. Okay. So, what is the shape? The shape is like this. Okay. So, you need to practice a little bit to understand how this is done. And now, if you want to write a program which can automatically do this, okay, that means I am giving you the vertices of the obstacle, you have to find out the C space obstacle. Okay, what is the logical way of doing it? Now, as in the previous case, we said in the previous case which is shown on top, okay, it is very clear that there was only one inclination here. Okay, the other faces are perpendicular to the x and y axis, so it does not cause any angle. So, if I take a vector which is perpendicular to this surface, then this vector appears here, and this is my line corresponding to this side. That is very clear. Now, what about this one? Suppose I take this line. Okay, suppose I take this one like this. Okay. So, this fellow, this side is coming where? It is coming here. Okay. So, this is the first side. What is the second one? Let us take the second one. The second one is here. So, this is my normal. So, where is this coming? That is coming here. Okay. Where is the third one? The third one, let me change the color. So, the third one is this one, which is coming this side. Okay. So, where is that fellow coming? That is coming here. Okay. So, each of these three normal vectors that I have drawn, they correspond to one of the sides. Okay. So, each of the sides are causing an inclination, one here, and one here. Okay. So, we see that if there are three inclinations here, then there are three angles here. Okay. In this case, there was only one angle, so there is one angle here. So, there is very strict correlation between them, and the program can actually find out which side corresponds to the other one. Now, there is a standard procedure for doing that. Okay. This is called the star algorithm for polygonal objects or polygonal obstacles. Okay. Now, how do we proceed? So, we proceed in this way. What we do is we draw normals to each of the sides. So, I draw my normal E1, this is my obstacle. Okay, this is my obstacle. So, I have E1, E2 in clockwise direction, E1, E2, E3 and E4. Okay. Then I draw this circle. So, I draw my circle, okay, and mark each of these normals E1, E2, E1, E2, E3 and E4 clockwise. So, mark E1, E2, E3, E4, okay, normal to obstacle surface, okay, in clockwise direction. So, in clockwise direction. So, I have marked the 3 normals, then in the circle you mark this E1, E2, E3 and E4 in clockwise direction again. Then what do we do is we go to this triangular robot and we see that where are the normals corresponding to each of the surfaces. So, I am going to draw one normal here. So, where is R1? R1 corresponds to this surface, which is this one, it is in this direction. So, it is normal to this surface. Okay. Next what I am going to do is I am going to draw a normal which is corresponding to second surface, which is R2, which is here. Okay. Then I am going to draw another one which is corresponding to the third one. Okay. So, there are 3 sides of this triangular robot. So, these are my 3 sides of the robot. I draw one normal here. So, this one is normal corresponding to this is normal corresponding to this, and this is normal corresponding to this. Okay. So, it is R1, R2 and R3. Okay. Now, I draw the corresponding normals onto this circle now. So, R1 is here, R2 is here and R3 is there, exactly the same you can see. So, R2 was pointing in this direction. So, this is also R2. Okay. So, now what we have is in this circle we have the obstacle plus the robot, okay, the normals of obstacle. So, normals of obstacle plus normals of the robot. And if you look at this circle, what we can see is that it gives an indicator of where the inclination of this C space is going to come. Okay. So, this is corresponding to this figure now. Okay. Please look at this carefully. So, we start off by saying that if you look at these 2 surfaces. So, let us look at let us start off with where is R1? R1 is here. Okay. This is my R1. Okay. R1 is here. So, R1 is going to appear between E2 and E3. So, inclination due to R1, okay. So, inclination due to R1 will appear between from here it is saying. So, R1 is here, it will appear between E2 and E3. So, E2 and E3. Okay. So, the 2 sides E2 and E3, E2 is here, E3 is here. Okay. That means somewhere here it is going to appear. So, where is R1 going to appear? R1, the effect of R1 is going to come here. So, that is because of R1. Okay. And which is my E2 and E3, this is my E2 and that is my E3. Okay. Now, similarly if I look at the effect of R1, what about the effect of R2? So, inclination of R2 will come between E4 and E1. Okay. So, where is E2? Where is E4? On this figure you see E4 is this side. So, E4 is this side, that is my E4 and this is my E1. So, the effect of R2 will come between E4 and E1, and where is so it will come on this point here now. So, where is R2? So, R2 is in this direction, this is my R2. So, the effect will come here. So, that is my R2. Okay. So, we have finished R1, this is R2. Now, what we are left with is R3. So, the effect of R3 will come where? Where is R3? So, R3 is between E1 and E2. Okay. So, where is R3? R3 is here, it is between E1 and E2. So, R3 will come between E1 and E2. Okay. So, where is E1? E1 is here, E2 is here. So, R3 will come there. What is the direction? This is R3. So, we can see that it is coming at that point, and this is my R3. Okay. So, from this circle we were able to figure out very accurately that where these inclined surfaces are going to come in my C space obstacle. So, this is an automatic way of which is called the star algorithm for making C space obstacles, just by looking at what are the inclinations of the robot surface and that of the obstacle. Another example, we can have a look at this, where we have the star algorithm for this object now. Now, this one in the previous case, okay, please note that there are 3 inclined surfaces. Okay. So, there were 3 here. So, there was one here and one here. So, there were 3 of them. Now, in this robot there is only one inclined surface and 2 of these surfaces are perpendicular to the axis, okay, that you can see. Okay. So, we do exactly the same thing. I put E1, E2, E3 and E4. So, mark E1, E2, E3 and E4, okay, on the obstacle. So, mark obstacle. Okay. Then what do we do is we mark the robot. So, this is my robot. So, let me enlarge it, it looks bigger here. Okay, this is okay. So, it is bigger now. So, I mark R1, which is this side perpendicular to this R1, R2 is perpendicular to this surface R2, and R3 will be in this side. So, this is my R3. Okay. Similarly, I make my circle marking E1, E2, E3 and E4. Now, if you note, because R1 and R2 are perpendicular to axis, they will be aligned with the vectors which are with the normals of the object. So, you can look at R2 is aligned with E4 and R1 is aligned with E1. Okay. That means that there is no angle here, no angle or no inclined surface here. There is no inclined line here. Why? Because this R1 and the other one R2, they are perpendicular to the x and y axis, that you can see here itself, right. So, this is my x axis, that is my y axis. Now, so two of them are gone. So, there is only one left. Where is there one fellow left? That is my R3, and it is appearing between E2 and E3. So, R2 will have an effect between E2 and E3. So, on the figure, if you see where is E2 and E3, it is here. So, R2 will come this side. So, R2 will come there, and what is exactly what you are getting here. Okay. So, on this line, when the robot comes like that, this is my point which is going to slide, and it will be perpendicular to that. Okay. So, it is between E2 and E3, and this is my line. Okay. So, this is my line, and we get the other fellows do not cause any inclination. So, it is becoming like this. Okay. So, this is my C space obstacle. Okay. So, automatically geometrically we are supposed to do this, because at the end of the day it is a program, and a program or an algorithm will actually needs to compute this automatically. So, what is the input to the algorithm? The input to the algorithm is the obstacle. Obstacle means vertices of the obstacle, then the shape of the robot, the vertices of the robot. Now, they are geometrically, this is a rectangle and this is a triangle, right, geometrically. So, essentially what the program can do is it can construct this rectangle, it can construct this triangle, and based on that it can find out the shape of the C space, okay, C space obstacle, and that is what geometrically we have done, and we were able to get it to this point. Okay. Now, so this is showing an object which is having 3 inclinations. This is showing an object which is having, this one is showing only 1 inclination. Okay. Now, we said that the rotation angle of the robot here, the robot had theta equal to, let us say, 45 degrees. Okay. In this case, it had theta equal to 0 degrees. The robot is not rotated. Okay. You can see that in one case the robot is like this, the other case the robot was like that. Okay. That means, and please note that the shape here is like this. This is the shape, and in the previous case the shape is like this. The shapes are different. Okay. That means for every angle you will get a different shape. Okay. So, please note this, that as the robot rotates, okay, and it can rotate from 0 degrees to 360 degrees, and for each of this it is actually infinite. Okay. It can be if you want to divide 0 to 360, you can make infinite divisions, okay, small divisions. So, let us say that we are making divisions of 1 degree, okay, because there will be changes between each of them. So, let us say we are making divisions of 1 degree, so there will be 360 divisions, and for each of this you are going to get one shape. And if you get one shape, what will happen is for one shape you will be getting a particular shape of your C space. So, if you proceed a little in this way, that for every theta we get one shape of C space obstacle. Okay. So, if you stack them all one on top of another, what you will get is something like this. Okay. Let us say this is corresponding to so this is my x axis, that is my y axis, and this is my theta axis. Let us say it starts from 0 to 360 degrees. So, when theta is equal to 0 degrees, what you will get is a shape like this. So, this is corresponding to 0 degrees. Sorry, this is not 0, this one is 0. So, corresponding to this one, this is my shape. Okay. So what you will get is one shape which is like that, which is the theta equal to 0. Now I change theta equal to 1 degree. Okay. It can be 0.1, 0.2, 0.3, but that makes it very, very difficult. Okay. And it will get computationally very, very expensive here. So in path planning, we have to also talk about the computation cost of path planning. So in path planning, if the computation cost is very, very high, it will take very, very long to compute. So here we just put 1 degree intervals, and for every 1 degree we get one of these surfaces, and then we stack them together. So this is my C space obstacle is a volume. Okay, so please note that this is not this is a volume now. It is bounded by patches of ruled surfaces. Okay, so it is bounded by these surfaces here, and this is called ruled surfaces which are bounding my C space obstacle, which is a volume now. Okay. That means for a robot which can rotate, so a robot that can rotate plus translate, okay, will be getting a volume. My C space obstacle will become a volume, and the volume will look something like this now. Okay. So I hope it was clear how we got this and how we can automatically generate this kind of surface. Now this is an example. This is the same example drawn x, y, and theta, where the now something else to remember here, I forgot to mention it here, is that the obstacle the origin of the frame, the local frame, is here, x and y. Now suppose, so this shape that we have got here, this shape that we have got here is corresponding to a robot which has theta equal to 0 and origin given here. Okay. So if I change the origin to some other point, if I change the origin to some other point, suppose I change the origin to this point now, at the center of the robot, or let me change it here. This is my x, let me rub that off, and this is my x, and that's my y now. Okay. What will happen to the shape? The shape will change. Okay. Why? Because we are tracking the locus of this origin only. So what you can do as practice exercise, you can actually change the origin and see what will happen to the shape, and you will see that the inclination surface will now change. Okay. And the full shape of this is going to change. Why? Because the origin has shifted now. Before we were tracking this point, now we are tracking this point. So let me go back a little bit here. Yeah, let me go back here. Suppose we are tracking this point, what will happen is now it will become like this. Okay. Because we are tracking the base point now. So you can see the shape is changing. Okay. So there will be one inclination surface only, but then the shape is changing of the whole C space. It has come this side now. We are tracking this point. Why? Because my origin is here. Okay. So if this is my origin, then the shape changes to something like this. Okay. So in that case, what will happen? My origin shape will become like this. It will come like this, like this, like this, and like this. Okay. It remains more or less same, but this will change position because the origin has shifted now. Okay. So this is basically showing us that if you change the origin, this fellow's shape will also change corresponding to a particular obstacle. So the obstacle here was a rectangle. So similarly here, if I change my obstacle here, then what will happen is I am going to track this side, so that is going to change. So this shape will change a little bit. Okay. So now what you can do is, as practice, you can try and change the origin and see what is going to happen. Suppose I put the origin in the center, okay, then what is going to happen? Okay. So that you can actually draw and see. Okay. Now this is a case we are talking about the volume. So C space volume that has been obtained in exactly the same way. We start off with theta equal to 0, and then theta equal to up to 360 at intervals of 1 degree each, and then we stack them and we get a shape like this. So if I am doing motion planning now, if I want to go from here to here, I have to find some way by which I can go from here to here. Okay. So this is the meaning of C obstacle or C space obstacle. So in short, it is called C obstacle. Let us look at this simple example before we proceed. Is for a robot which is having a rectangular robot, and I want to do path planning of this rectangular robot, that I want it to go from some point to some other point. Now just for practice, let us draw the C space of this. So this is my robot, it is inclined at 45 degrees, this is my obstacle. So, can you draw the C space of this C obstacle for this particular case? So, if I take my robot and I place it in different locations around this, which is very clear, you can see. Okay. What will happen is, and if I please note the origin is in the center. So, if I mark the locus of the origin, then I will get a shape like this. So, this is the boundary to which the robot robot can go, the rectangular robot can go with respect to the obstacle. So, if I look at the locus of the CG or the center point of the red rectangular robot, then I am going to get a shape which is like this. Okay. So, if I combine it, I get my C space. So, this is my C space, C obstacle, okay, which is my green part, and then I can do motion planning of this C space obstacle. Now, once you have made that, now this robot obviously can have different angles. So, theta can be anything from 0 to 360. So, which also means this will also change, this shape will also change in 3D. Okay. So, when we are talking in terms of all the angles, this shape will have some kind of a shape in 3 dimensions, and I want to do the motion planning of that shape. Okay. So, how we can proceed is essentially, let us look at the robot is in this configuration. Okay. Theta equal to 0 degrees, and I draw the C space. Okay. I can draw the C space. So, you can very easily draw the C space here. Okay. So, the robot can come like this, the robot can come like this. Okay. The robot can come like this. So, if you track the center point of this, you can draw the C space. Okay. So, you can try doing that. Now, if I incline the robot a little bit, okay, then the C space becomes like this. Okay. So, if I keep rotating this robot with different angles, the C space is going to change, and if you combine all of that, then we get the full C space volume, the C volume, or the C not C space, sorry, C obstacle volume. Okay. So, I get my, this is my C obstacle, not C space. Now, let us look at a goal path planning problem here. So, the path planning problem is that I have 2 obstacles, and I have a robot which has to go from Q goal to Q start. This is my start, and this is my goal point. Okay. So, it has to go from here to here. Okay. So, how do we start? We start off in this location by looking at by drawing the C obstacle, and my C obstacle is like this. Now, once you have drawn the C obstacle, I can very easily connect this to this, and I know the robot can go now. Okay. So, this is a way by which, for this particular robot which is inclined like this, it can go from here to here. This is a path, there are other paths also, and the robot can go in all these paths. Okay. So, the robot could have gone like this also. Okay. But this is only for a particular theta equal to 0, let us say. Okay. Just for example, if you say this is theta equal to 0, then this is corresponding only to theta equal to 0. Now, if I have theta equal to 45 here, okay, then my obstacle C obstacle will look like this. Okay. Now, how do I go? Is there a path? Yes, you can see that there is a path like this. Okay. So, even if the robot is inclined 45, it still has a path. Okay. Now, so for different inclinations, I can actually combine all of them, and I get some kind of a shape. This is my C volume, C obstacle volume. Okay. So, this is my C obstacle volume in 3D. So, this is my C obstacle volume, where theta, for every theta we get a particular shape, and I have this. Now, if I want to do path planning from some point to some other point, I have to find suitable ways by which I can go. Okay. This was an example of particular angles, but I can combine all those angles, get this shape, and then also do this is an example of a 2D rigid object moving using C obstacle at different orientations. So, this is my shape of the object, shape of the robot. These are obstacles. Okay. Now, if you want to go from here to there, okay, then basically it can go like this, like this, like this, like this, and at every location it is actually changing its angle. So, it has to go back here and find out what is the shape corresponding to that particular angle, and then move. Okay. And it can do that continuously, and you can go from one point to some other point. And this is the old the historical problem of the piano movers problem. So, we have a piano, and the piano has to move. So, exactly for different angles of the piano, we can find out what is the C obstacle, and then correspondingly move it and take it from one position to another position. Okay. So, this is how the piano movers problem is solved, and for a robot which can have any shape, which can have any angle, you can actually go from one point to another point by choosing angles suitably, okay, such that you do not hit the C obstacle. So, today's discussion was about generation of C space obstacles, and we discussed about C space obstacles and automatic ways using the star algorithm, and how path planning is done with a C space obstacle was explained today. So, we will move on tomorrow to what to do. So, all this discussion is about to move to serial robots, which are a little bit more difficult. Thank you.